Section 7.1 is zero and negative exponents. I can simplify expressions involving zero and negative exponents. Big ideas here. We can extend the use of exponents to include zero and negative exponents. If we look on page 418 to start here, it has a zero and negative exponents. Take note. First part says zero as an exponent. For every non-zero number a raised to the zero power equals 1. So it doesn't matter what our base is unless it's 0. If we raise it to 0, we always get 1. For every non-zero number a, an integer n, a raised to the negative n power is going to give us 1 over a raised to the positive n. So we change our exponent to be positive by moving it to the opposite part of our fraction and just changing the sign there. So we went from negative to positive. If we'd have had a negative in the denominator, we change it positive by moving it to the numerator, and it works the same way. Okay, so to change it from negative to positive, and we're not talking about the value itself, we're talking about the exponent, we move it to the opposite part of our fraction. So from numerator to denominator, or vice versa. Example 1 here is simplifying powers. What is the simplified form of each expression? So right now we have 9 raised to the negative second power. We need to change our exponent to be positive by moving it to the denominator in order to be able to calculate it. So we keep our base exactly as it is, just change our exponent to be positive. And what this means is that we're taking 9 times itself 2 times, or 1 over 81. In B, we have negative 3.6 raised to the 0 power, and we know that anything raised to the 0 power is always just 1. Now, feel free to pause here and give these a try if you'd like. What is the simplified form of each expression? Here we have a negative exponent, so in order to make it positive, we move it to the denominator and change the sign. Again, our base doesn't change, our exponent changes signs. So we're taking is 4 times itself 3 times, 4, 16, 64, and we get 1 over 64. In B, we have a base raised to 0 power, and that's always going to be 1. 3 raised to the negative second power, again, that negative exponent we're going to try and change so it's positive so that we can calculate our value here. So we move it to the opposite part of our fraction. Right now it's in the numerator. Remember, if we see a number, we always know it's over 1. So it's in the numerator, we move it to the denominator, change the sign on that exponent, and 3 times 3 gives us 1 over 9. In D, I have 6 to the first power, negative first power, so I move it to the denominator, so it becomes a positive, which means I just have 1 over 6, just 1/6, so 1/6 there. And in E, negative exponent, so we move it to the denominator to make it positive. And again, that negative 4, our base didn't change, so it's still negative 4 squared. That's important, because what it means is that we're taking negative 4 times negative 4. And that's going to give us a positive 16. So 1 over positive 16. Make sure if you type that in your calculator, you put the parentheses in before you square it, because whenever we square a number, it's going to be positive. An algebraic expression is in simplest form when powers of the variable base are written with only positive exponents. So in example 2 here, we have 3 separate things. We have a 5, and we have an a cubed, and we have a b to the negative second. These are 3 different things. So I can write this as 5 times a cubed times b to the negative second. And we're only going to move things if they have a negative exponent. So my 5 can stay. My a has a positive 3 for an exponent. It can stay. But my b has to be moved to the denominator in order to make it positive. So again, my 5 and my a can stay, and my b moves to the denominator and becomes positive. Keep in mind that the 5 and the a didn't have to stay together. They're their own individual pieces. So we could have moved the a without having to move the 5 there if it would have been negative. For b, I have x to the negative 5th power in the denominator, and I'm trying to make it positive in order to have it simplified. So we move it to the numerator, x to the positive 5th, and all I have left in my bottom is a 1. And in the numerator, I had 1 times that, but we know that 1 times anything is itself. So we get x to the 5th power. Simplified form here. Again, feel free to pause and give these a try if you'd like. We have a negative exponent, and I'm trying to make it positive in order to have it in simplified form. So I'm going to move it to the denominator and change the sign. We move it to the opposite part of the fraction and change the sign. If we don't have anything in our numerator, remember we still need the 1. We need to show it's in the denominator by having it underneath our fraction bar and a numerator. In b, we have the opposite. We have the negative in our denominator. So we have to move it to the numerator to make it positive, to change that sign on the exponent. Again, it's over 1, and we still have 1 times that n cubed, but 1 times anything is itself, and anything divided by 1 is itself. So we just get n cubed. Here for c, I have 3 different pieces. I have a 4, I have a c to the negative 3rd power, and I have a b. And those are all individual factors. Okay, we can treat them differently based on each individual factor's exponent. The 4 has a positive 1 exponent. The c is negative, so we need to move it to the denominator. And the b is positive. So I keep my 4. I move my c in order to make it a positive 3, and I keep my b, which again has a 1 as our exponent, which is positive. So 4b over c cubed. And in d here, we have 2 over a cubed. The 2 I can keep where it's at, but my a to the negative 3rd power, I have to move to the top in order for it to be positive. So a cubed. And I have nothing left in my denominator. So 2a cubed there. E. My n, I need to move in order for it to be positive. And my m stays because it's already positive. I only move things if they're negative. And again, we need to show those are in the denominator by putting them underneath our fraction bar. If there's nothing in our numerator, we put a 1. Okay, again, my m is already positive, so I don't move it. It stays in my denominator. My n is negative, so I need to move it down to the denominator to make it positive. It doesn't matter. We also could have had our m listed first. That's fine, as long as we keep our exponents with our variables. So the 5 has to stay with the n, and the 2 stays with the n. Okay, so it doesn't matter the order in which we list those as long as we keep them together. In example 3 here, we're going to be evaluating an exponential function. My 3, I can keep. It doesn't have a negative exponent. My s, I can keep. It doesn't have a negative exponent. But my t, I have to drop down to my denominator to make it positive. Now, it doesn't matter if we change them before we substitute in or afterwards. I personally think it's easier to do before we substitute in because there's less things that we have to remember. We don't have to remember parentheses or negatives or things like that as we're moving them around. But if you think it's easier to substitute in first and then move things around, that's totally okay. Again, because my exponent was negative on my t, I had to move that to the denominator. Now, I know what s and t are, so everywhere that I see those, I'm going to plug in the values. Instead of an s, I'm going to write a 2 to the 3rd power. And instead of a t, I'm going to write a negative 3 squared. PEMDAS says that we need to do parentheses first, nothing I can simplify, and then exponents. So 2 cubed is 8. And negative 3 squared is positive 9. Negative 3 times negative 3. Again, anytime we square something, it's positive. This is going to give me 24 over 9. when I multiply, and I can take a 3 out of each of those. 24 divided by 3 is going to give me an 8, and 9 divided by 3 is going to give me 3. So 8 over 3, or 2 2/3, or 2.6 repeating. Again, here, go ahead and pause and give these a try if you'd like. I have a negative exponent on my n, and I know I'm going to have to get rid of that in order to simplify, so I'm going to move that to the denominator. I also know that w to the 0 power, as long as it's not 0, which it's not, is just going to be 1. So right now I have 1 over n to the positive 4th power. I can substitute in my values. Here I know that n is negative 2, so I plug in negative 2 to the 4th power. Negative 2 times negative 2 is 4, times negative 2, negative 8, times negative 2 is positive 16. So negative 2 to the 4th power is a positive 16, so I have 1 over 16. Here I have n to the negative 1st power, so I'm going to move it to the denominator in order to make it positive. And my w squared is already positive, so I keep that in my denominator. I'm going to substitute in the values that I know here. I know that n is negative 2, and that w is 5. According to PEMDAS, I have to do exponents first, and then multiply, and I get negative 1 over 50. N is negative 2, and w equals 5. Here, for C, I know that n to the 0 power is just 1. And w to the 6th, w is already positive, so I can just keep that the way it is. When I substitute in 5 for w and take it to the 6th power, I get 1 over 15,625. And again, I knew what w was, so I plugged that in for w. In D here, I have two variables. I have two pieces, two factors. My n stays because it's a positive 1. My w I have to move to the top. Because it's negative, I move it to the numerator to make it a positive 1. So I have a w over n. W is 5. N is negative 2. So I get negative 5 halves, or negative 2.5, or negative 2.5. A population of marine bacteria doubles every hour under controlled laboratory conditions. The number of bacteria is modeled by the expression 1,000 times 2 raised to the h power, where h is the number of hours after a scientist measures the population size. Evaluate the expression for h equals 0 and h equals negative 3. What does each value of the expression represent in this situation? So h is the number of hours after a scientist measures the population size. So for h equals 0, okay, that means time 0. That means right when they measure for the first time, like when our experiment starts. And we plug that in for h, so 2 to the 0 power. We know that 2 to the 0 power is just 1. So this is 1,000 times 1, which is just 1,000, and this is bacteria, which is pretty gross if you think about it. And that's when it starts, when the experiment starts. Now, for h equals negative 3, that means 3 hours ago. So 3 hours before the scientists started measuring, that's how many bacteria there were. So we have 1,000 times 2 to the negative 3rd power. I'm going to move that negative exponent down. So I'm going to have 1,000 over 2 cubed, which is 1,000. 2 cubed is 8. And here I'm going to get 125 bacteria. So 3 hours before it started, there were 125 bacteria. Quick recap for section 7.1. We can extend the use of exponents to include 0 and negative exponents. And that's all I have for section 7.1.